Hello, so today I'm going to be talking a bit about the forcing feedback relation. This is used within climate science, climate physics, and so I'm going to talk a bit about what forcings are, feedbacks, some examples, and why they use this and what it's for. And this is because essentially, within climate physics, normally you want to see the energy balance and discrepancies, and then you see from some type of perturbation within their system or some type of external factor, and you see what happens to your system. So we'll talk a bit about more of that. So this equation right here, this is the forcing feedback equation, and this equation is actually a Taylor expansion. So if you were to Taylor expand this around temperature, like so, and then you can also keep going right here. However, normally this is not needed as much. This right here normally is just set equal to 0. Of course, it can keep going and going. So in this equation right here, we will normally set this right here, the first term, the initial term, is the forcing, while this term right here is the feedback. The feedback, and actually this right here specifically, this term is lambda, which is like the climate feedback parameter. So this is actually done within the unit for this is normally watts per meter squared. So looking at like the energy flux with this, and as I said before, this is normally used within climate physics because we're looking at energy discrepancies and energy balance. So essentially what we can do with this is we would take the change of energy to be equal to 0 from this after we add some type of forcing, and we see how the equation balances out. So essentially we have some type of forcing, and then you have the feedback trying to bring it back to 0. So another thing with this is a lot of times as well, many of these simulations will be in like fixed SST, or at least to begin with. If this is the case, that just means that the sea surface temperature, as this right here, or the temperature is equal to 0, change of temperature. So there is no feedback. So that would mean that the change of energy is equal to just the forcing. So going forward, looking at the forcing. So as I said before, it measures the imbalance of the Earth's energy balance caused by some type of perturbation in the system or some type of external forcing. So this could be, for example, a boundary change like topography, the land, CO2. This could be aerosols, etc. There's lots of ways it can be. This kind of reminds me, I'm not sure if this is the best example, but it kind of reminds me of a harmonic oscillator. So if you push it from its state of equilibrium, and essentially what happens from there. I don't know, that's kind of how I think about it a bit. But if we were to look at that for a radiative forcing, we could look at, for example, this would be like RF, radiative forcing. People or sometimes will use the effective radiative forcing, which is normally considered the best metric for some type of radiative forcing difference, which is normally taken from the IRF, the instantaneous radiative forcing, plus the sum of the adjustments. And of course, and when the change of the temperature is equal to 0, then that would mean that the ERF is only equal to the change of energy, where this is equal to the change of N perturbated of the system minus the end of the control. the perturbation being adding some type of external factor, such as CO2, aerosols, or more of them. So, from this, the IRF, the instantaneous rate of forcing, is essentially what instantly happens after looking at the perturbated system. So, what this means is if we were to look at the Stefan-Boltzmann equation, we could have the change of surface temperature minus the change of temperature of the stratosphere would be equal to the IRF. This would be like if, for example, we added aerosols into the stratosphere. The IRF is going to be the energy flux, the radiative flux of this. For the adjustments are taken of temperature. This temperature could be surface, atmosphere, stratosphere, etc., etc. Water vapor, which is represented as a Q, and the albedo, which is represented as alpha. And these are the direct responses to a change of the atmosphere or surface state from a forcing, a perturbation. So an example of this would be, let's just say we have some type over here. We have some type of radiative flux right here from the surface. This is going to be here from Stefan-Boltzmann equation. And then let's say that we have up here we have some aerosols, and this is in the stratosphere. So that this way when it comes up, and this is a aero equals the change of T strat power 4. So we know is the forcing of the aero is much less than the surface, and the difference of this is the IRF. The adjustments from this would be, for example, when you have this right here is much larger than the aerosol. So where does that energy go? It doesn't. At least right here, we're saying that the energy is conserved. So what happens is that the temperature adjustment, so AT, is going to actually increase, because as the aerosols absorb and then re-emit the radiation from the ground, the infrared radiation, it will then increase the temperature of the stratosphere. And because the temperature is increasing from the cloudy, I'm forgetting the name, but because the temperature is increasing, the water vapor concentration would also increase. Although this one would be much smaller than the temperature increase. So let's look at feedback now. So the feedback is essentially the feedback is a natural process that increases or decreases the forcing, the climate forcing, or the initial perturbation within the system. So, for example, if the change of N goes to 0 or equilibrium, then we could say, if we were to have a scale, we could say that this right here is a change of surface temperature. We say that this is a change of N. We have some type of forcing, which is right here. The intercept, as the system tries to go back to the change of energy being 0, or of course this right here would be 0. Right here, we can see a decrease going down, and it's going to be adjusted by its surface temperature. And then this slope right here is the climate feedback parameter, or F. So what does this mean? As we were saying before, the change of N is equal to G dt, the derivative of this. And so what does it mean? So as the order tries to stabilize itself, the Earth can then regulate itself by changing the surface temperature up or down in order to go back to a state of equilibrium. So if we were to do like an example of this, we could have something that goes in and it comes out, and then the feedback is sort of like this. It's a picture on Wikipedia that might be helpful. So normally the climate feedback parameter is negative. However, what happens if it was positive? We have change of T here, change of N, and we have some type of forcing right here. And it goes up, and then some nonlinear dynamics right here. Make it stabilize or something. This right here would be like a runaway effect, similar to Venus. So this would be like a runaway effect. This would be like what happened at Venus, which is interesting. I recommend looking up. So going back to the equation, the forcing feedback equation, I hope this helped you better understand the equation. The equation is pretty straightforward, but of course getting the forcing or lambda, the climate feedback, is not always easy. And yeah, I hope you all have a wonderful day. Let me know if I got any mistakes, and thank you for listening.